should introduce myself. Well, you can see up there, Peter Ashman, University of Adelaide. I'm also seconded from the university to HILT CRC as the program leader for their cross-cutting technologies program. So we've got some great speakers today. I'm just trying to, if I took some notes here somewhere. Got some great speakers coming up. In this session, we're going to move slightly upstream from where we were before lunch. And we're also going to diverge our focus a little bit. In the previous session, we heard mostly about upstream processes for dealing with low-grade ores. In this session, there's still a strong focus on green iron and steel, but like in the previous session, towards the end, we'll start to hear a little bit more about some cross-cutting technologies that can be applied across multiple sectors. So expect to hear a little bit more about lithium, alumina, cement and lime, thermal storage, and some more other topics. For the discussion, please feed any questions through Slido, but I'm keen to see if we can get a bit of a dialogue going, particularly this late in the afternoon. Remember, the themes of the conference are barriers, enablers and pathways, and so I'd like to try and distill some key outcomes under these categories. Before we kick off, I hope he's in the room. I just wanted to thank Craig Garlick from University of Newcastle for stepping in for Tom Honeyans and for getting himself to Adelaide at very short notice. Tom had some issues he had to deal with, and so Craig stepped in and will be presenting on Tom's behalf. So thanks, Craig. It was much appreciated. So without any further ado, I wanted to introduce our first speaker, which is Sara Hornby, founder, Global Strategic Solutions, to talk about ramifications of Hydrogen-DRI EAF steelmaking. Thanks, Sara.
Hopefully my voice won't give out before the end of this, but thank you very much, Peter, for the introduction, and thank you also to HILT CRC and to University of Adelaide for inviting me here to the HiTeMP. I'm going to talk about the ramifications of Hydrogen-DRI EAF steelmaking and the implications potentially of the ores. There's no real significant issues making, operating DRI shafts at 100% hydrogen. The problem becomes when we try and process the DRI through the electric arc furnace, especially if we're going to 100%. The challenges are potentially the gangue and the lack of chemical energy in the DRI. Now, new production processes are coming to the fore, which hopefully will alleviate or postpone or circumvent some of the issues that we have, but we will see. So this presentation is going to address the challenges, the motivators to start with, and the challenges, and then the enablers or not. And before I look at some emerging technologies very quickly, and hopefully I can do it in 20 minutes. It's a very large subject. So the industry motivators are basically the requirement of 0.2 tons of CO2 per ton of steel moving forward for the Paris Accord. And currently you can see, hopefully this will work, over here. At the bottom here, I've put the actual CO2 tons for each of the 4 steelmaking processes that are the 4. Currently, 70% of the world is blast furnace BOF steelmaking with 2.2 tons of CO2 per ton of steel, moving right the way through to the EAF. The Europeans, with the potentially lack of natural gas, have pushed for the Hydrogen-DRI process for them moving forward. The IEA is promoting various percentages as we move to 2070, as you will see. But the 100% scrap is actually rated at 0.38 tons of CO2 as it stands currently. And if you increase the amount of renewable energy going to an EAF, that will drop significantly. And with Hydrogen-DRI EAF, it will drop to 0.02. 100% scrap EAF is challenged moving forward because of the availability of good, clean scrap. So the motivators: producing clean steel through an EAF. There's a lot of blast furnace operators that will challenge whether it can actually be made through an EAF. You need to maximize scrap to keep your CO2 levels down, and your prime scrap, as you can see from the, from the bottom chart here. The obsolete scrap is going to grow significantly over the years, predominantly because China is going to be dumping between 40 and 500 tons of scrap, a million tons of scrap into the system, with the requirement to reduce the residuals that are going to be increasing with the continuous recycling of the scrap. We're going to need to use DRI, HBI, pig iron to basically dilute the residuals that are coming through in the scrap. The problem is that you're going to have an increasing amount of CO2, as you can see from the middle chart. As you increase the percentage of the OBMs, you're going to increase your amount of CO2. And pig iron, of course, is a clean source, but that's going to drop from 1.35 billion tons down to about 0.2 billion tons moving forward. So the question will be whether there'll be any pig iron. The arc furnace operations currently are predominantly based on the chemical energy from carbon, and it can be as high as 25–30% sometimes. And that chart that's up there, I believe it shows 23% of the 45% chemical energy is coming from the carbon. The CO evolution from that carbon in the system is stirring the bath. It's improving the contact between the foamy slag that it creates and the metal. It's cleaning up the steel. It reduces the FeO in not only the DRI that's being fed in, but also the slag. And you can see that it will also decrease the consumables and the cost of making steel. The in-situ carbon that you find in the OBMs is much more efficient, 95+%. When you've got the injection or charged carbon, you're only getting between 24 and 76% of efficiency most of the time from those being added. It's also being added using carrier gases, and you also have all of the sulfur and the bad entities in the carbons. So carbon's basically reducing the kilowatt hours, the electrodes and refractory wear. It reduces the FeO in the slag, which is a big concern because that's the biggest contributor to the cost of steelmaking, basically. Now there's new plant injection trials shown on the bottom, and I'll go through this a little bit more later. But they found a way of making the injection carbon 98% efficient. And just as an FYI, the coal only contributes about 2% of the EAF emissions. The impact or importance of DRI in the EAF melting is basically consistency, lower residuals, and predictable chemistry going in. The heat generation from the reactions forming CO and from the reduction of Fe3C are also contributing to the system. And the CO is flushing the nitrogen, hydrogen from the steel. The carbon's neutralizing the FeO in the DRI also. And just an example, 95% met, 93% iron total at 1.8 or 2% carbon will have an excess of carbon in the actual DRI of 0.75 to 1.75. And that will add to the chemical reactions in the system. The DRI also alleviates issues of sourcing irons. In countries such as Argentina, it's very difficult to get any scrap, certainly not any good scrap, for example. There's some quantified benefits at the bottom there from ArcelorMittal in Montreal. They said 1% carbon was basically going to improve your yield, meltdown kilowatt hours by 25%, and it was going to reduce the electrodes wear. The Energiron chart on the right-hand side actually shows a comparison between 4.4 carbon and 2% carbon, and they actually found the 37 kilowatts per ton reduction using 1% carbon, 11 kilograms of carbon reduction, and also 4.5 minutes off power on time. Gang has a big impact on what happens in the arc furnace, and this is a chart from a paper that David Trotter and I et al. Wrote way back when, and it actually quantifies a dollar value for every 0.1% of the gangue that's in an iron, if you add it all together, although you wouldn't have that in a situation, you're looking at close to $1 per percent, $1 per ton if you've got 0.1% of each of these being added to the furnace. Now, Nucor had shown back when 50% use of DRI actually could reduce some of the kilowatt hours and the tap-to-tap time better than the 100% scrap that they were running. Part of this is due to the fact that they had to look at their standard operating practices and improve them significantly. So in most places you won't see this kind of improvement, but they actually showed a lower meltdown energy, and they showed a drop from, excuse me, from 421 to 408 kilowatts, and they saw a drop of 61 to 59 minutes in tap time. In Mexa, just as a side, showed that there was actually quite a lot of gangue in a scrap charge, and I'll show you some how that can be beneficiated a bit later. So that's 4.25% in scrap. Other benefits from DRI come from charging it hot, where you can get 20 to 30 kilowatt hours per 100 degrees C, drop in kilowatt hours. There was a paper we wrote back when I was with Midrex that showed continuous feeding was worth almost $30 per ton because of the improvement in actual tap-to-tap time. And there's a yield increase when you put it in instead of low-grade scrap in some of the countries where scrap is not necessarily available. And the high percent carbon DRI is better for refractory life and yield. Any DRI or HBI that's going, or even pig iron that's put into any system is going to increase the CO2. So challenges. Basically, you have zero carbon DRI in zero carbon in the DRI if you're going to use 100% hydrogen to produce it. It's going to basically, therefore, reduce the foamy slag that's in there. It's going to reduce significantly the reaction times that are occurring. You're going to have to put in more slag formers to deal with the gangue. That's going to increase your cost not only for the slag formers, but also for the removing the slag and dispensing of it. You're going to have no bar stirring. You're going to have higher kilowatt hours because of that. You're going to have to physically put in some kind of stirring mechanism to the arc furnaces to enable the reactions to occur. You're going to have much higher kilowatt hours due to the greater electrical power input that you're going to need to heat your slag that's going in and being twice the volume. And the melt temperature actually increases with the lower carbon in the steel. There's also going to be a much longer meltdown time and tap-to-tap time, which is going to basically lower your yield, and that's a big financial incentive, is to increase your yield and throughput productivity. There were 2 trials done with the Circa Red zero carbon HBI that came out of Trinidad at the North Star Steel plant in Texas. Basically, they confirmed all of the thoughts that we had. You need a large heel, continuous feeding. They needed more kilowatt hours, carbon, oxygen, and pig iron to melt the charge. The oxygen and carbon injection was needed to control the FeO in the slag and in the DRI, and to stir the bath. The higher pig iron was required to help melt efficiently. They had issues in making the low nitrogen requirement from the plant. That was due to the lack of flushing from the CO that was being, or wasn't being, created. They had to delay the oxygen injection to make sure that they could keep the furnace operating properly. And, sorry, I'm looking at the time here. SSAB has actually melted some of the hybrid zero carbon that they've melted, that they've produced in Europe, and they melted it in the US of A, and they actually found no problem, but we don't know how much pig iron that they were charging at the same time. Supply is, there's insufficient green power. Hydrogen production, 1% of what was produced in 2022 was green. It's expensive, up to $10 per kilogram, which makes it impossible. I'm going to skip through some of this. Ore is not available. We're saying that 3 to 4% of the ore is good for DRI production through the EAF, not through the DRI plant. And scrap, of course, the guarantees on chemistry are not there all the time, and we're going to have more obsolete moving forward. And biocarbon is going to be an issue. Whilst there are operations out there that supply the biocarbon, that's going to probably be insufficient for the future. Conversion costs is another big issue. The IEA numbers that were put out in 2015 through 2018, I calculated $1,327 per ton of liquid crude steel. And that's much higher than any of the other operations that they put out there, the smelt reduction through to the blast furnace BOF. The CRU in Europe actually calculated $3,700 per ton of steel. And they said that $300 per ton carbon tax would be needed to incentivize 90% of the European steelmakers to convert. The other issue, of course, is the cost of conversion. We're already not competitive with the rest of the world, and that's the graph at the bottom. If you look at the data, I think this was August, the USA is producing hot roll band at $839, Western Europe at $680, the world in general is at $580, and China's at $448. So we've got to have some taxes to ensure that the non-compliant, non-green nations are going to pay for not converting, obviously. And the ETS in Europe is predicted to be around about $128 a ton by 2030, and the CBAM could be $216 a ton. This is a conversion cost done by Boston Consulting. Very quickly, they used natural gas at $9 a gigajoule. Hydrogen was at 6.3 a kilogram, $78 per megawatt hour, and the DRI pellets were at $154. Yes, natural gas HBI is down at 0.68 tons of CO2, and the green hydrogen is down at 0.2, but you've got a $660 cost for the hydrogen DRI versus $140 for the natural gas DRI. So the question becomes, are the carbon taxes going to justify the difference in the cost of making hydrogen? Process enablers, there's a definition there, I'm not going through it, but my perception that greening the steel industry and the government's involvement, there's a lot of R&D funding. I don't know much about Australia, but some of the other parts of the world. There seem to be decisions made that are uninformed and based on name recognition as opposed to actual technical prowess. The technical education is required. We need to have more involvement from the technical side of the industry to ensure that we have no investments put into non-scalable, non-starters moving forward. This is improving. We've seen a lot of change in the United States in the last 5 years. So hopefully we will solve the problems quicker than expected. We need to promote and assure, of course, as we've heard over this last couple of conferences, that there needs to be a lot of infrastructure put in place, without which we're not going to be able to move forward. We need the rich ores availability if we're going to go through the EAF route. There's a big ore, high iron ore content in Quebec, and they can't get it to the basically seaway at an economically viable proposition. And several companies have tried to do that. I think also we need to look at further R&D with industry, especially not only with the green, but also greening the brownfield sites a little bit more. Partnerships developing with industry. HILT has a great example of what should and could be done and is being done. I think the other thing we need to do is change the steel industry's mentality. There's a major blockage there to moving forward and changing. New technologies, the ESFs are thought to be the solution to the future with the lean ores that are out there. Tata, Europe, ThyssenKrupp, Voestalpine, of course, BlueScope and POSCO are looking at this, whether it's going to the BOF or to the EAF or pig iron to the EAF. But they need to upsize the technology, they need to change the electrodes from carbon, and they need to improve the carbon footprint in general for that technology. Scrap mills are back integrating into scrap ownership to ensure quality control and the supply moving forward. Shredding scrap has been shown in the UK to densify the material, clean it up to 98% yield from about 89%, which is quite significant. They also managed to reduce the copper that was contained within the scrap, and it became a significant improvement. The other thing that they found that they had a fair, substantial sales value for the fluff coming out of the shredder because it's non-ferrous content. New ore processing and remediation. Of course, Sara's got the lime magnetite pellet process that's potentially going to pilot. And there's new DRI processes coming from Calix with the flash DRI production. And also there's a new operator that's doing a study right now on a 50,000 ton a year plant called ferrous silver. And they're going to use basically the biochar from agriculture and forest waste with CCUs. And they believe they'll even have a 0.875 sink for CO2. New technology tools, I'm not going through all of this, but basically the Canadian companies found a way of doing supersonic injection of carbon. The finer, the better. And they've got up to 98% efficiency with the carbon and with biochar. So in summary, the Hydrogen-DRI EAF steelmaking is viable, but moving forward, we need to have lower cost green steel, lower cost green energy, green hydrogen, better ores that we can put through the EAF. The DRI can go through a DRI plant, no problem. It's the EAF that's the issue. It's going to be uneconomical unless there's a lot of government support moving forward. The zero carbon is going to mandate some significant changes to the standard operating procedures in steel mills. And with less carbon to remove, the EAF emphasis is going to be on gang removal and control of the phosphorus and the other residuals in the liquid steel. New technologies are in the wind, and looking at the future, I think that we're going to be melting lean ores in an ESF or something similar to that, or we're going to have to remediate the ores and put that through the EAF with some hydrogen. But the hydrogen needs to be kept to possibly 80% only, which will give us carbon in the DRI plant, and it will facilitate melting in the EAF. I'm sorry, I'm over. Thank you.
Thank you. Sarah's apologising because she went over, but it was only by less than a minute, I think. So well done, Sara. Okay, next talk, as I mentioned, from Craig. So thanks very much, Craig, for joining us at very short notice. Craig's presenting some work from the University of Newcastle on behalf of Tom Honey and the team, of which Craig's a member. And the title is Lab Scale Electrical Smelting of Hydrogen-Based DRI from Australian Hematite and Goethite Ores. Thanks, Craig.
Okay, thanks. It's nice to be here and see a lot of familiar faces that you only get to see every year or two. So Tom couldn't make it. His father has taken ill, so he's in New Zealand with him now. But I'll do my best to stand in for him and tell a good story. Laboratory scale electric smelting of a hydrogen-based DRI produced from Australian hematite goethite iron ores. It's a bit of a mouthful, but it's all the good words are in there, okay? This is our mission, it's pretty clear. So the team there is at University of Newcastle, Tom, myself, Sara Mooney, Tejbir Singh, Damien O'Day and Harold Rogers too, who some of you will remember. So we've all had a hand in working on this project. Okay, I better try this thing here. Or is it just the green one? Green button. Okay. Okay, sweet. Okay, so this next slide here, Tom's put that in because we've changed our name at what was originally BHP Central Research Laboratory, and it's had several name changes over the decades. But most recently, we've returned to the title of the BHP Centre for Sustainable Steelmaking Research. And yes, we're still located at the University of Newcastle in the same old central research laboratories. The SSR is a member of the Australian Research Council, Steel Research Hub, and SSR contributes to the heavy industry low carbon transition, the HILT Cooperative Research Centre. Okay, Tom's put some points in here as the presentation outlined. I might stick to some of those, but we'll see how we go. So really for the last 3 years or so, we have, with BHP, set out to develop our laboratory facilities at Newcastle University and also our personnel so that we can do research into the performance of Australian iron ores in hydrogen reduction and smelting of it to make a hot metal product. That's been our key focus last 3 years. BHP has sent us on that mission fairly early in the piece, and just earlier this year, ARENA has come on board and put their support behind us as well. So we're reasonably well funded, and we've come a long way in the last couple of years. This next slide here is one that the BHP people put together, but it captures so many of the issues that face the iron and steel making industry and the supply of iron ore to it. You know, we have the challenges of you know, for Australian iron ores, the blast furnace process followed by oxygen steel making, it works just fantastic, right? Why would you change it? But okay, change we must. So there are some alternatives to do that. One of those is to, as Sara has told us about, really is to melt scrap. You know, if you've got scrap, by crikey, go for it, because that's the best way to reduce your emissions. But there's just not enough scrap. Okay, so for the 70% of the steel that is made worldwide, not through the electric arc furnace, we've got to do something about that 70%. It's not just about the 30% that goes from scrap melting, okay? So what we're about is on the 70% of the problem, okay? That's what we work towards. And just for you, Mark Pounceby, the geology is important, but so is the metallurgy. Okay, and the gangue and the slag produced from it is a big part of the story. And so while the beneficiation crowd want to take out that gangue and throw it on the ground, what we're saying is that direct shipment ores have got a great source of gangue materials in them, and the cement industry wants it, right? So you know, somewhere there's a happy solution in there that serves both the iron and steel industry, the iron ore industry, and the cement industry, and what's good for the world in terms of trying to reduce emissions. So there are some blast furnace alternative pathways, nicely captured in the BHP slide. So the challenge of beneficiation ore is difficult for hematite goethites, which Mark has told us all about, and I believe him. Okay, so for this reason, the DRI ESF route, and I was pleased to hear Sara mention those words, ESF. I haven't heard her say that before, but I was pleased that she did so. And the process is attracting quite a bit of attention, you know, from some of the big players, okay, from POSCO, from Tata Steel, ThyssenKrupp, etc. Yeah. And our own BlueScope Steel and Rio Tinto and the BHP who've, you know, made a partnership to try and do something. So attracting quite a bit of attention. And I suppose being at the, you know, partly attached to the BHP arm that funds us, the customers of Australian iron ores, you know, they want an alternative to the blast furnace, okay? They say they want an alternative. So our mission is to look for solutions. So we're looking for solutions. Yeah. Tom likes to share this shelf slide of the Finmet plant because he was heavily involved in it in those early days of the 2000s. Now the thing about the DRI iron plant was that it made a lot of HBI, so 6 million tonnes or more. And so, you know, we do know a fair bit about this particular problem of trying to make, you know, gas-reduced, direct-reduced iron. And of course, the Badari plant had some operational issues, forced its closure. But a lot was learned along the process, along the way. And the one thing that really sticks out in my mind for that process was really about the yield loss that had to be taken in beneficiation to make such a product, right? What an enormous yield loss. And it was so high, I'm not going to say it, right? But the yield loss in beneficiation, big problem. So, so it really is an interesting point, and I'll come back to it. The other interesting development on the scene at the moment is the Finex plant with POSCO and you know, their efforts to change that into the Hyrex plant, which is the hydrogen reduction version in fluidised bed. And so you know, their objective is to use the medium grade ores, you know, 62%, put it through their process, so avoid that beneficiation step which suffers the yield loss. And so for me, David Trotter, dig and ship will be a sensible thing to do for some time to come. So we've got to work out how to do it. So POSCO's Finex process is a good comparison to make with the Finmet plant. But I think the Finex plant and certainly the Hyrex have perhaps set their targets a little bit lower in terms of running a lower metallisation, which avoids many of those sticking problems that we'll face with the Finmet plant. This one here is a little bit about some of those things that happen with hydrogen reduction of iron ores. So to do it without sticking is the challenge, and I've seen a lot of that emphasis in the posters that I've seen at lunchtime. So a lot of people are thinking about that problem. But you know, no doubt that lower temperature, lower metallisation is certainly going to be something that helps in that mission to avoid the sticking. Zero carbon DRIs, these are a handling challenge for sure. We'll have to work out what to do with that. However, back on our theme, smelting to hot metal is a possible pathway, you know, DRI, ESF. So even though you may make some DRIs that are quite reactive and present shipping challenges, if you can just take it and smelt it, you solve a lot of problems directly. So in the last 2 years, we did start some work to do hydrogen reduction of the Australia's iron ores at Metso Outertech in Frankfurt. And so we've tested those in fluidised beds in the 50mm batch and in the 80mm continuous process. Parasat, yes, I remember correctly. And so, yeah, those ores, direct shipment ores, work quite well, okay? And we were able to do that to get high reducibility without sticking. And so we were happy with that work. And in some ways that spurred us on to move in to try and do some of that hydrogen reduction of iron ore fines directly at University of Newcastle. So we've taken some lessons from Metso and we're doing some of that ourselves now. This is an example of some of that hydrogen reduction work. And Tom was simply wanting to show here that you know, we've taken some BHP MAC fines, reduced at 730 degrees C, and he's wanting to say that we've got a uniform reduction through both hematite and goethite grains, and most importantly, no whiskers or dense iron rims were observed, you know, which were known to be a problem for the sticking issues in Finmet. Right, so now we get onto the good stuff, which is the smelting part. And so DRI feeding an ESF to make hot metal may have its place in integrated steelmaking operations, right? So the integrated steelmakers are interested. It has some advantages for lower grade material and lower metallisations. Low FEO slag process is what it is. A little bit higher than blast furnace, but certainly nothing like a steelmaking reactor. The iron yield from mine to steel product is very high. You know, if we take that simple option to handle the gangue by smelting it to a slag. Slag potentially useful for the cement industry. The gangue in the ore is a plus. It is a lot better in concrete than it is sitting in a tailings dam. Okay. Electrode smelting. Oh yes, I think Tom put up this slide 2 years ago when he was here. But the key point here was that at that time, and probably still now, there were really only 3 real examples of electric smelting furnaces to make hot metal. These 3 here, which we've talked about, the New Zealand Steel operation, the one that was Highveld Drobus Steel, and the one in Steel Dynamics, Indiana. So these three guys know something about it. And the New Zealand Steel furnace in particular is one that I know something about, having worked there for quite a few years. Last key point here is that we can handle a big slag volume. So if we've got lots of gang in the ore, you know, we can handle the slag quantities. So typically New Zealand Steel, 400 kilograms per tonne hot metal. Highveld was at 1,000, and the Steel Dynamics is quite a special operation. They run around 70. So there's a lot of interest. So electrode smelting at laboratory scale, holy hell. Well, that's a bit of a challenge. So how do you do that? So electrode smelting has its key feature in that the heating is from the reactor centre out to the sidewall, right? Whereas most of our high temperature experiments that we may have done along the way have been in tube furnaces or induction furnaces or things like this where you know the heating mechanism is from sidewall to centre. So it's not those furnaces are not what you want when you're trying to study electrode smelting furnace, right? Electrode smelting is heating centre to sidewall. So that's what we've tried to do in our test work at University of Newcastle. We started small, which I did talk about a couple of years ago at the last Newcastle symposium. We started out with, you know, wire feeding in a welding circuit type operation, but quite quickly we progressed along to, you know, trying to work with an actual carbon electrode, DC electrode, single electrode, and so we're now up to around 5 or 6 kilograms is our charge size, and we're able to do it quite successfully. So of course electrode smelting, because you're heating in this mode of electrode centre to sidewall, the temperature gradients that we have in the smelting reactor are really very large, laterally from centre to sidewall and also from top to bottom. Okay, so that's what we try to deal with. And being a pyrometallurgist, you know, we always say, oh, what temperature did you do it at? And I say, well, mate, it's just a reactor full of very big temperature gradients. And so to talk about a single temperature is really a bit of a false argument. So you're dealing with a smelting system that covers very wide range of temperature. Okay. So a little bit more about what we've done at Uni of Newcastle. And of course, one of the challenges of trying to do these experiments is that because you've got such a hot zone of heating in the middle of the reactor, measuring the temperature is a real challenge, right? So trying to measure the temperature anywhere under that arc heated volume is just impossible. But we can measure temperatures over by the sidewall and a little bit in from the sidewall. Okay, so that's what you see in that graph there, giving you a bit of an idea about what the temperature profile looks like in a typical one of our tests. Okay, so we start with a cold charge, fill up the reactor volume, strike up that arc, and find that we get a molten pool very rapidly, you know, within 10 minutes. And then the temperature stabilises a little bit, and we're able to do some extra top feeding which in some ways simulates real-scale electric smelting furnace. And we're able to take metal and slag samples in situ as we progress through a run, okay? So we're doing all these things. And it's an exciting experiment, and we've done about 60 of them now, so we're getting good at it. Oh, okay, Tom has animated this one, so there's a bit of after animation for you. Okay. Righto, in this slide here, trying to take shots inside the furnace like this is also quite a challenge. But some of us are brave enough to put our phones in there and try and take a picture. Okay? And so if I can see if I can make this thing go by pressing something. Oh, there you go. So there you go. There we are looking inside that furnace. You can see the electrode there that's immersed in the slag layer. You can see the arc that's sparking around underneath. It's quite a thrilling thing to look at when you're trying to do it. But immersed electrode smelting. So we're able to do this, right? So it's not just about striking up a plasma arc on top of a slag. It's actually we're able to turn off the plasma and do some submerged arc smelting. Okay, real process stuff. So it's good stuff. Okay, so the Hydrogen-DRI that we're now making at University of Newcastle, we set out on that mission to make that specifically so that we could have something to feed this electrode smelting furnace, right? So for some of you who are down the journey, you'll know that, if you want to smelt this stuff, you've got to be able to make it. And there are some challenges just to make it. And the hydrogen costs money. And so if you go too big in your reactor size, then it's going to cost you a lot of money. So at 5 or 6 kilograms charge size, this is okay. We can manage that money required. So we do this. And this size is convenient. You can do a lot of tests in a short amount of time. And you don't need to get all of the various company interests talking on the same stage to agree what you should do. So we're doing our own thing, and that's what we do. And for the moment, we keep going, and we're going flat out. This graph here is showing you transient metal composition. The top curve there is for carbon content in metal. We're able to get the carbon up above 3%. And the bottom curve is showing you, I think it's silicon content. And we've got some results at different power density, okay? So power density is part of the deal of controlling the temperature gradients within the reactor. And that's, that's real process stuff, and it's good to be able to do those tests. Slag compositions. Slag compositions is a real challenge in this type of smelting reactor because, we've got metallic shot in the slag, we've got FeO that's in the slag, we've got other ion units that are there as unmelted DRI. So we've got all these things going on. So if someone says, well, what slag Fe are you running? I say, well, which Fe were you really talking about? So we make this graph, but there are some caveats about what it really means. Yeah. And we've done some stuff at a little bit bigger scale. So in March this year, we spent a good month at Aachen University in Germany. As it turned out, we had made some hydrogen-reduced DRI finds in Frankfurt the year before. So we had some material there that was left over, and so we said, let's just try and smelt it in Germany because it's too hard to try and ship it back to Australia, etc. So we did that, took it there, and the Aachen journey was interesting. It's a twin electrode AC furnace, 120, 200 kilogram type size. We learned some interesting things there and came away with a set of results. And basically, we need to go back and do some more work there. But there's probably enough encouragement in the results that we did get to say that we should go back. So after they've done some extra things to improve their off-gas system, we probably will go back and do some more. Am I out of time? Okay, so just to refresh there, so okay, we've started at lab scale, we've done a bit of intermediate scale, we'd like to do more. And of course, you know, there are those other activities that are happening at the larger pilot scale and demonstration scale. So, you know, we're also involved in those, and, you know, whatever we learn at the smaller scale, you know, we're wanting to, you know, take some of those lessons into the bigger scales. Yeah? So the conclusions there, if I can just read those. Yeah, so the electrode smelting furnace is really the focus of this work. So, you know, if you put on your rose-coloured glasses and you can see renewable energy for electricity and low-cost hydrogen, then, you know, this process is a winner in terms of trying to use the medium-grade iron ores that Australia has a lot of. So good from that point of view, good for Australia, and hopefully good for the decreasing emissions in the iron and steel industry, you know, on a worldwide scale. So, okay, so that's about all I wanted to say. Just to acknowledge the support that we've had from BHP and ARENA. Thanks to Metso Autotech in Germany for helping us along the way. And that's it. Thanks very much.
Thanks, Craig. Okay, so our next talk is from Martin Smith, Business Development Director at Primetals. And Martin's title looks like it's Smelter, Processing Australian Ore in Carbon-Free Steelmaking. Thanks, Martin.
Hi, thanks. Good afternoon, everybody. Yeah, I'm continuing the theme. You'd have thought someone quite smart would put these presentations together. I'm going to present on what we as a technology company see as the solution. So I'm not going to focus on the research and development. I'm presenting slides prepared by one of my colleagues, Gerald Wimmer, who is the head of converter steelmaking inside my company, and it's his team who's responsible for the smelter moving forward for us. I'm setting the scene a little bit like my predecessors, make a few points about the numbers that we're facing in this transition period. I'm not going to claim we've all got the same numbers, but I do think we've got the same trends, and the trends say that the fantastic blast furnace route that we know and love needs to change, and we need to find a solution to that. And looking at options, considering the options that we've got, thinking about the iron ore that we've got available to us, I see two fundamental ways forward. On the left-hand side of my slide, you can see the traditional route using, let's say, low to medium quality iron ores. On the right-hand side, you can see an argument that the high quality iron ores suit a shaft-based DR process coupled with an electric arc furnace. I like this slide. I like this slide in two directions because it's very easy, very common to read the slide downwards in the sense that it says, got this material, this is how you should process it. But it also works upwards as well. Got this flow sheet, this is the sort of material that you need. But what we do need then, I think, moving forward and echoing the theme of my predecessors, is a solution for poor quality raw materials and the shaft DR furnace. And to do that, the one-step process that is well accepted with the high quality iron ores where we can process in a shaft furnace, go straight to electric arc furnace, is not going to work with low quality raw materials. And that's why I then make my point of a two-step process, two-stage process. I then introduce the smelter. that we've been referring to on and off for the last few minutes. So in my flow sheet then, I've got a shaft-based DR system processing low, medium quality raw materials. The product passes through the smelter, and the molten material from the smelter then gets transferred to a BOF. Transitions, I'll show very quickly on this slide. The grey at the top is our established blast furnace BOF route, and we can transit then to the two options. But the beauty then of or should I say maybe the advantage of going from traditional blast furnace BOF to smelter BOF is that we can retain the BOF in our flow sheet. And that offers advantages then for secondary steelmaking systems that are based upon a particular heat size that match with a casting machine. All of this is being retained and stating the bleeding obvious isn't having to be changed at great or even greater expense than we're already facing. If I look at the smelter then, and I want to get into, having gone through my set the scene introduction, a little bit more detail about how we see the smelter working. So on this slide, I've got inputs and outputs. So obviously we're focused on getting the DR, but what we really want to do in the flow sheet that we envisage is have a hot DR connection. And that offers some strong thermal benefits to the performance of the smelter. You'll also notice that I'm capping the cold materials that I'm adding, like the cold scrap and the cold DRI, because it just impacts on the thermal balance that we see. I wouldn't see these numbers as absolute, the world will end if you go to 11% type of a basis. But it just gives us some logic to how we can set the system up. This process with the smelter is going to be a reducing process. That to me, when I thought initially about the traditional electric arc furnace and what we're looking at here, that's the big difference as I see it. That's the thing I focus on a lot about how it's going to work, and it offers advantages as well. But we're producing a reducing gas. I've got some ideas on let me say, gas cleaning on a subsequent slide. We're also producing a liquid metallic product, which I've also mentioned already, but also a liquid slag, which can be used with a granulating system to produce cement-grade material. Thinking about the size of the smelter, it's got to match with the size of the DR unit. And I've got a range of DR modules shown on the slide and matching them with various sizes of smelter. I think the key point to take away here is that, get up to about 2.5 million tons per year on the shaft furnace, and you're going to need 2 modules of smelter. And that's because that's the size we think we can get to at the moment. But history surely has told us already that the limits we've put in place, we've already broken them. 100 years ago, you'll never have bigger than a 500 cubic meter blast furnace, and look where we are now. So I give you those limits today. I fully expect in the years to come we can challenge and exceed them. If I compare the electric arc furnace process with the smelter process. So there's a lot on this slide, and I don't have time to go through it, but we're switching the way we think about how the electrodes work and how they react with the materials in the bath. We're changing, I think, from an electric arc furnace with a quite a small volume to a smelter which is almost like a blast furnace hearth in terms of its size and the volume of liquid that we're playing with there. If you just look on this slide, as a nice 3D image of what a DR smelter combination would look like. This is like a 2.5 million ton per year DR facility. So I have got two smelters shown on the drawing, and the drawing's also showing a hot connection. So we go direct from the DR system straight into the smelter through some feed systems. It's hot, the smelter's hot obviously, so we need a cooling system. I want to just spend a few seconds on that. It's a sealed system, so My simple sketch on the right-hand side is trying to show how we've got various types of water cooling covering the roof down the slide, a bit of intensity around the slag area, and then back down to the bottom of what I referred to like as a blast furnace hearth a few minutes ago. We're showing on this particular design here like an underhearth cooling which is using air, which is like a bit of a backward step to where we are on the blast furnace now, but proven for many, many years on the older blast furnaces that we used to build. It's just a consideration of risk. How dangerous would it be if we had a breakout at the bottom with water there that we can't get to? So risk that I was at the conference last week. Risk. It keeps coming up again, and this is our example of risk management. Something that we're concerned about. This is how we want to handle it. I mentioned the gas cleaning, reducing atmosphere in the smelter, like I said a few seconds ago, so we can produce a gas that we can collect and use as a fuel. So the upper half of my slide is showing like a BOF LD gas recovery system where we can switch over when the gas conditions are right. We can collect the gas and use it as a fuel. When they're not, we can flare the gas. Or on the bottom half of the slide, we've got heat recovery. Instead of collecting the gas, we just burn it, generate as much heat as we can, and then use that heat to generate some energy of some sort of steam or steam directly into electricity. So we've got options there that go beyond the smelter itself to make the flow sheet more interesting. So where are we at as a company? References in the previous slide to Finex. Well, we're moving on to Hyrex now with POSCO. So Hyrex is in the middle there. Hy4 is our development at Voestalpine Steel in Linz. It's the next stage of the Hy4 test facility that we built at Donowitz. Sometimes you'll hear it referred to as Hy4 Smelt. Because we're actually building a smelter in conjunction with that facility. Hyrex system has a smelter as well. And on the left, the Midrex system, with the flexibility to have natural gas or hydrogen as appropriate. So I need to wrap up. My conclusion, the transition has started as we see it. In the last few weeks, we've had contracts with Dillinger and Blaster for various types of Midrex units. Blaster is a hydrogen-based, and Dillinger is a Midrex flex, so it's got the facility to change from natural gas through to hydrogen. We see it that hydrogen-based direct reduction. It's an important part of the next step for the industry. We want to be there. I'm here as a technologist. I feel as if I'm a rare part of the audience here, but that's what I need to do. I need to sell my technology to my customers, and we want to have the variable or the various options necessary to satisfy all the different customers that we're going to need. So a lot of ours will contain, that my customers will have to deal with, will contain gang materials. The answer is the smelter. And that smelter, we see it as a high-capacity unit to replace the blast furnace. Very quick, I think. I hope you've got a feel for at least where we see the smelter in the future of the business. Sorry, just a little bit.
Thanks, Martin. Next short talk is from Chris Bumby from Victoria University of Wellington, talking about New Zealand's Hydrogen-DRI program. Thanks, Chris.
Hi everybody, green button. Thanks for having me. I've got 10 minutes to tell you about a program that we've been working on for 5 years, so I'll try and go quickly and just touch on a few different things. I have to say I feel like a little bit of a fraud, or at least somebody bringing coals to Newcastle in New Zealander coming to Australia to talk about iron ore. You guys are a much bigger organisation, much bigger supplier than we are, but we have a little bit of a story of our own, and we certainly have some research experience that I'm hoping to share. So I'm going to talk about some work that's been funded by the New Zealand government. It's included a lot of collaborators from a research perspective, and we've also done some work with the University of Newcastle and Tom Honeyans and Craig, who mentioned some of that work earlier. There we go. Before we start, just remind the audience where New Zealand is. We're not Australia. We're a separate country. There's about 5 million of us, and we have one of most things. We have one cement plant, we have one methanol plant, we have one aluminium plant, we have one urea plant, and we have one steel plant. It's not very big. It's about 650 kilotons a year. It's based in Glenbrook, and it's responsible for about 5% of our gross CO2 emissions all by itself. So it's attracted a bit of political attention, as you might imagine. It's also owned by BlueScope, so it is actually an Australian asset in that regard. And it's unusual, and I'll come to why it's unusual in a minute. But one of the things that's unusual is it's possibly the most picturesque steel plant you've ever seen in the world. That is the steel plant. It has views out over the harbour. It sits in the fields with pastoral land on both sides and flax and native trees. It's actually a very interesting place to go and visit and to work. And we're situated in a country which has about 85% integrated renewables in our grid already, and with several gigawatts of known wind and geothermal available for further installations. So in the context of electrification of industrial processes, New Zealand's quite an interesting place to be. And we have an ETS, which has a carbon price and a sinking lid on industrial allocations, all of which is interesting. But we work with a very unusual iron ore. So in New Zealand, our iron ore is an iron sand. It's a beach sand. You can find it all the way down the west coast of the North Island, and it's a titanomagnetite. So it's got about 8% titanium in it. And that is substituted into the lattice. You can't leach it out. You can't wash it out. It's inside that magnetite spinel lattice, which means that you have to process it pyrometallurgically. But one of the nice things about it is that as a beach sand, it's a bunch of very spherical, quite homogeneous particles. And that'll come up again later. The sea has done all the work for us. We didn't do this. This is a couple of millennia of the sea just wandering around. There's a modest amount in a couple of existing mines, but there is an awful lot sitting on as sands off the coast of New Zealand, and we are interested in the ability to unlock that as a commercial opportunity. But that titanium is a problem. You can't put it in a blast furnace. We've known that for a long time. The first 100 years of history of steelmaking in New Zealand was abject failure. We got to 1950, post-war, and the government put some money in and said we need to do this properly. And they developed a process called the New Zealand Steel Process. And that's what's at Glenbrook now. It is a DRI, ESF, and at the moment, BOF process. So we've had a lot of people talking about potential systems, and that's where the steel industry might be going. New Zealand's been doing this for nearly 50 years. However, the caveat to that is that we are running coal-fired kilns, and that means that the current process is actually pretty CO2 intensive. It's about 2.5 tons of CO2 per ton of steel. What we've got is coal and sand coming at the front. We've got kilns. We've got these two melters. I've put this picture up. Craig's already shown it once today. Well done, Craig. At every conference I've been to on this topic in the last couple of years, I've seen at least 6 other talks with this picture on it. If you see it, this is our smelter. This is the New Zealand Steel Smelter. It's the one that you find online. Everywhere, there's one other one as well. And this is it in operation. Then those melters go through a unit called a vanadium recovery unit. And that's kind of important for us. We've got about 0.5% of vanadium pentoxide in the original titanomagnetite. And that vanadium recovery unit takes off a vanadium-enriched slag, which is about 1 to 1.5% of the world's primary vanadium supply from this little tiny steel plant. And that's relevant too, because what New Zealand Steel and BlueScope are about to do is they're about to put in an electric arc furnace into this system so that they can increase the scrap utilisation, which is great from a CO2 perspective, but it means we're putting half as much iron sand in, which means it's putting half as much vanadium in, which is producing half as much vanadium-enriched slag. Vanadium is a critical metal. It would be ideal if we weren't doing that, but from a dollar's perspective, it doesn't make much sense to do anything else. So the question is there a future for a hydrogen-DRI in this system? We've got a beautiful modular system already. In principle, we could delete the coal and kilns and put in a hydrogen-DRI reactor, and then the ESF is there, and away we go. So that all sounds great, but we've got this weird material that no one else has looked at, and so fundamentally there's some R&D that's needed to be done. And so that has been what has been the focus of our work over the last 4 or 5 years. Before I move on from this slide, one thing that I'll come back to later in the talk as long as I have time is to note that That hydrogen-DRI reactor just shows hydrogen coming in, and I've ignored the rest of the system. It's really important to remember that any of these H2-DRI systems need a hydrogen recycle system, and I'll talk some more about that later. Another thing that's really important to bear in mind when we're talking about research and then trying to join it up to industry is just scale. It is really easy to get lost in scale when we're having talks that span from materials science through to large-scale industry and engineering. There's a scale of 1 million between some of the experiments we will do in our lab and what is practically required at the industrial scale. And that means that you need to be clear about what you are and aren't studying when you're looking at these systems. So in the sort of context that we're operating in over here, our R&D is largely about a fundamental understanding of materials behavior, fundamental understanding of chemical reactions, fundamental data which can feed models. What we are not doing is we are not doing validation of heat and energy balances. We're not doing specific technology validation. That requires a lot more money and, to be honest, a lot more hydrogen. So down here, we're able to operate with 1 or 2 bottles. These units here, these are all test units in our lab. We've got a vertical shaft reactor, we've got a batch reactor, and we've got a test fluidized bed reactor, and we're building a bigger fluidized bed reactor at the moment. These systems are all able to run on bottles of hydrogen, either a single bottle for very small systems or multi-bottle, 4-bottle manifold is what we tend to run over here. The moment we move up above this sort of 10 kilogram an hour of DRI samples is the moment we are moving into large amounts of hydrogen. You are talking about a tube trailer or a dedicated electrolyzer pretty quickly. And so that becomes a significant percentage of the total investment that's required for any plant. And it's another reason why you're moving out of what would be considered an R&D environment and very much into bespoke technology development. So we've got 2 separate streams going on at the moment in terms of the program. We started off looking at pelletization. It's a nice, easy process to use. In principle, it's well established, and it should be relatively forgiving for a large range of different materials. And we've also been looking at fluidized bed for the obvious reason that those beautiful spherical particles I showed you earlier fluidize very nicely. We've got various capabilities in the lab, and this slide is largely just to publicise to the researchers in the room that we have this equipment, and please come and talk to us about using it. Where are we going? There we go. Right, so I'm going to very quickly skip through some data. I know there's a lot of people here who are not technical people in the room, so we'll just move very quickly. But just talking about moving through some of the scales, some of the early work we've done is looking at pellet scale work and looking at kinetics. You'd be stunned to realise that these reactions go very fast. Hydrogen is a very small, zippy molecule. It reacts very quickly with other things. So we see shrinking core type kinetics in our systems, and we can identify kinetic models. What's interesting, of course, is the moment we move to a larger reactor to make material that we can test for other purposes, we then start to move in fixed bed reactor dynamics, and so what we actually see is a reaction front and often channeling between the pellets. That's a function of being at this intermediate scale, which is not a proper reactor and not a single experiment, not a single pellet either. But that does allow us to make enough material to do other tests. So this is some data that Sara, one of my PhD students, was showing in the poster session. You may already have seen it if you talked to her. But we've been able to look at generating large numbers of pellets and doing ex situ strength tests. And one of the things we find about this particular material is that because we've got all this titanium that we exsolve as we reduce the pellets, what we do is we form this very brittle ceramic structure inside the pellets, which means that our pellets undergo brittle failure even when they're fully metallized, which is not ideal if you were looking at something that you want to briquette at a later point. So we moved on, and we've also looked at making larger quantities of this in the vertical shaft, and then we've taken this to Newcastle. I want to thank Tom and Craig in particular for doing some melting studies. We've got a lot more data that I haven't shown here yet, looking at partitioning, looking at slag partitioning, and the ability to melt material that's coming out of our reactors and confirm that it will go through an ESF and it will incorporate carbon. But just moving quickly, we've also done quite a bit of work on fluidized bed reduction. This is showing our material fluidizing. It's a beautiful material to fluidize. It's got nice high density, 5 grams per centimeter squared, nice and round. And that allows us to put reasonable amounts of hydrogen through it, and we can do some process mineralogy, because both minerals and metallurgy matters. And when we do that, what we see is that we have a system where we form this system, and we can react it at very high temperatures, because as it reduces, it forms a titanium-rich skin around the outside. And so this is a situation where our contaminants are actually helping us. They're making it easier for us to run this reaction because they're coating the outside of the particles and they're preventing us forming wet liquid metal on the surface of the particles, which would otherwise make it stick. If you tried to do this with a Pilbara hematite, once you got up to about 900 C, this stuff would start to stick. But we're still going at 1050, no problem, which means that we can access really rapid reactions. Building a reactor you can run at that temperature is a secondary question, but the fact that it works is really encouraging. Here we go. Here's a picture just showing the titanium-rich shells on the outside of those particles. So just to move quickly on the other thing, one of the other things we find in our fluidized bed reactor is that at these higher temperatures, when we're doing a batch reaction, we run and we hit a stable water output. And that's because we are running at this boundary between the iron-Wüstite phase boundary. So we've effectively hit thermodynamic equilibrium, even though we're running in a little test reactor that's only about 40 millimeters worth of bed height and has got a gas residence time of a few hundred milliseconds. That is enough for us to get to the gas equilibrium in the system. Again, showing you just that this is a very rapid reaction. And that has ramifications for downstream design. It also means that actually our reaction rate isn't kinetically limited at all. It's just limited by how much hydrogen we throw in this regime. And so it doesn't matter whether you're going at different concentrations of hydrogen, different particle sizes, different bed masses, different whatever, you get the same answer. It's just stoichiometrically sitting at this boundary here until you put enough hydrogen in to do the reaction, which makes some of the modelling fairly easy. So I just want to finish off with some takeaway thoughts. I haven't technically run out of time, I'm afraid. Here's a model that I discussed earlier about having this hydrogen recycle loop in it. This bit matters, okay? If you're sitting at your thermodynamic boundary, that's about 35% for a cross-flow or 50% for a counterflow system. The rest of that's hydrogen. You cannot throw that away. You cannot afford to throw that away. You have to recycle it. So you need to put it through a condensing heat exchanger, which in principle sounds reasonable. But that needs to actually be able to handle some relatively high flows of material. And particularly if your utilization rate isn't up there, they can get really big. Hundreds of meters per squared heat exchanger per ton, which is really quite large. So bearing in mind that gas utilization really matters is something that's come out of the modelling work we've done on this and is, I think, more generally applicable outside of the work we're doing. Other thoughts that I think are worth just mentioning in this context is that ore contaminants aren't always terrible. Yes, they add more gang load to downstream melting, but they can help in certain powder processes. Collaboration is essential, and the scale up beyond the 10 kilogram scales that we're running in our labs at the moment is expensive for all of the reasons that we've previously talked about, and certainly in the New Zealand context, it's out of reach for most new research organisations and will require technology providers to lead. Thank you. Thank you.
Thanks, Chris. Okay, changing things up a little bit now, we have Matt Boot-Handford, Chief Scientist at Calix, and he's going to be talking about decarbonising industry through the electrification of industrial high-temp processes. Thanks, Matt.
Is that green button?
Yes.
Great. All right. Thank you, Peter, and thanks for having me. I'm going to talk to you about decarbonising industry through the electrification of industrial high-temp processes. So what I'll do is I will give you a brief introduction to Calix and its technology. I'll then talk you through the various different applications that we're applying the technology to and the projects that we're using to scale the technology to full scale. So looking at the Calix and Pilbara Minerals lithium project, the low emissions lime and cement technology for capturing CO2 from lime and cement, zero emissions iron and steel technology, or ZESTY, and then finally alumina. And then I'll finish off by talking through what we need to do to achieve what we need and what the support we need to achieve our goals. So this is the Calix calciner, the Calix kiln. It is, in its simplest form, it's an indirectly heated kiln technology. Pre-ground material is introduced through the top of the plant, so in a fines format. The kiln is indirectly heated through the walls. Any bound trapped gases are released in the process and exit through the top, and the product exits through the bottom. So key features are, because it's an indirectly heated process, it means that any gases that are released in the process are kept fairly pure unless we add in diluent. And this is a feature that we're exploiting for our low emissions lime and cement, or LILAC technology, in which when we introduce carbonates, so cement meal or limestone, the CO2 is released and kept fairly pure, so it's near sequestration ready. The other benefit of this technology is that it's electrically heated. It can be ramped up quickly, it can be ramped down, it can be shut off, it can be started up very quickly and shut off quickly as well, so applicability to grid balancing applications. We can also use the technology to affect other chemical reactions. So in the zero emissions iron and steel technology, we're introducing hydrogen in through the base. We're adding iron ore fines in through the top. Flash heating to promote the direct reduction of iron ore. So it's yeah. So anyway, that's all the various different applications. Oh, sorry. Okay, so there are several applications for this single platform technology, and we're applying it, as I mentioned, within cement and lime, for direct air capture applications, for the processing of hard rock lithium ores, alumina processing, and iron and steel. And I'll go through several of the projects that with which we're scaling the technology. So the first is the Sustainable Lithium Demonstration Plant, which we are, so Calix and Pilbara Minerals, a lithium miner in Western Australia, through a JV, are progressing a plant at their mine site in Pilgangoora. This plant is designed to process spodumene, so that's a hard rock aluminosilicate lithium ore. Processes the flash calcines the spodumene to effect a phase transformation that essentially pops open the structure, and that allows us to process using hydrometallurgical processes to remove the lithium and convert it to a salt. Yeah, so that's one of the projects doing. It's a 30,000 tonne per annum site. It's under construction, and the project objectives are to reduce the carbon intensity and transport and reduce transport costs. Life cycle assessment studies have found that renewable-powered electrical calcination of spodumene would reduce emissions by 90% compared to a conventional coal-fired rotary kiln, and 80% versus the natural gas fired rotary kiln. We're also planning to demonstrate lower capex and opex costs relative to rotary kiln processing, and we're also producing a higher value lithium product here onshore rather than shipping the spodumene offshore to China. So construction has commenced, and we're targeting production of the lithium salt next year. And here we can just show that site works have commenced, and construction is well underway. Okay, so next I'll talk about the LILAC technology, and I'll skip through that one because that's not actually relevant to electric calcination. But I wanted to just talk through the typical process that we're following to scale the technology within the lime and cement industry. So LILAC 1 is our first pilot plant, which was built in 2019, and producing 25,000 tonnes per year of CO2. It's currently processing up to 5% throughput of the host plant, and is one of the largest CO2 capture facilities from cement today. We're now scaling beyond that to a 100,000 tonne per annum scale, and that'll be built at a site in Germany, in Niglo, and that is processing 20,000 tonnes per annum, and we take a modular approach to scaling. So in this case, we have a single tube for the LILAC 1. LILAC 2 is a module of multiple tubes. The full scale will be multiple modules, and that's the LILAC 3, which we're developing several opportunities to process between 500 to 1 million tonnes of cement. Okay, so the next technology is our zero emissions steel technology, or iron and steel technology. So I went through a little bit about this earlier, but the key benefits of this technology are it's renewably powered and flexible operation. So the system, including the reactor, can be powered entirely by renewable electricity. No fluidized bed, so it's a lot simpler than a fluidized bed operation. We're targeting minimum hydrogen consumption. And by that, I mean we're able to provide all of the energy input for the heating through the walls, and so therefore we don't need to combust any of the hydrogen within the process. And the demonstration plant will include hydrogen recycle. We are processing lower grade ore, so I think we've processed down to about 53% iron in our process. We're processing iron ore fine, so no pelletization is required, and we're developing a scalable and flexible solution to scaling the technology to various different scales. This schematic just shows a schematic of the 30,000 tonne per annum demonstration plants that we're progressing. So moving on to which, we've completed a FEED study for a 30,000 tonne per annum zesty demonstration facility, and completed an extended ore testing program. We've completed over 130 tests with 9 Australian iron ores. We've been able to produce very high metallizations in excess of 95%. We just mentioned here that this is within our pilot facility, so this wasn't designed for the zesty process. It was a much shorter tube. The full-scale plant will be much larger. And so we were quite encouraged by these results. And just finally, techno-economics sort of analysis has shown that the low-carbon HBI from Australian iron ores are competitive with what we expect to be competitive with even or close to current HBI market prices. Finally is the alumina calcination process. So we've completed pilot plant trials on this study. We've also been working with HILT CLC on this as well to assess the technology relative to other calcination technologies, and found that direct electrification of the alumina calcination processes potentially offers the lowest energy intensity process. As I mentioned, we've tested multiple different sources of gibbsite. We've achieved smelter-grade alumina specifications, achieved very high concentrations of steam, so compatible with steam reutilization, mechanical vapor recompression, etc. And we're now seeking support from industry partners to support the scale-up and commercialization and demonstration of the technology at the next scale. So I've run out of time, but essentially we're progressing this technology. We are moving through to demonstrators on multiple different scales, and we need your support. We need industry-wide collaboration, continued investment into low-carbon technologies such as the Calix technology. And as well, I think one of the challenges we're facing, particularly with the zesty demonstrator, is identifying sites that have the renewable energy supply, the hydrogen supply that we need. And so support for enabling renewable energy infrastructure, green hydrogen, and technology access. So just finally, just a quick sort of promo for some of the other talks that we'll go through in a bit more detail. Some of the specific applications of the technologies. We've got Simon Thompson speaking tomorrow on the electric calcination technology and its applications for direct air capture, which I didn't really cover today. And then Sara from Swinburne University Technology, who we've been working with through HILT and Swinburne and University of Adelaide, will provide an update on the extended ore testing program that we undertook with HILT. Yeah, and I think I'll leave it there. Thank you very much.
Thank you, Matt. And our last talk before we get into the discussion is from Mahesh Venkataraman, Chief Technology Officer at 1414 Degrees, the future of clean heat, a low-carbon revolution for industry. Thanks, Mahesh.
Thanks very much, Peter, and thanks to the organisers for having me here. I apologise for the very clickbaity title over here. I don't select these. The marketing team is to blame for these. but my job is to justify that title during this presentation. So 1414 Degrees is a publicly listed company, Adelaide-based. Our workshop is here in Tonsley Precinct. Our focus is on the thermal energy storage for decarbonizing the hard-to-abate industrial sector. So we have one of our funding partners over here, Woodside, attending the forum as well. And we do have a good relationship with manufacturers like Refratechnic as well. So yesterday I was thinking about this presentation, and a lot has been said in the last 2 days regarding the need for the thermal storage. So I've basically removed half of my slides because I don't need to go through the importance of the thermal storage in the heavy industries. I wanted to talk about the bricks that we've developed. That's our thermal storage media. But I also thought it's much easier to actually bring one of these over here and show you guys. So if you're interested after the talk, they are lying in my backpack. Just a couple of sample bricks I carry around. So I want to go through the journey that we have taken in the last 10 or so years as a thermal energy storage developer. And the technology has its roots in CSIRO. The first system which was envisioned was concentrated solar thermal parabolic dish system with graphite encapsulating pure silicon as the receiver and a Stirling engine coupled to it. That was the first patent the company had. Plenty of challenges with this system. We moved away from that concept quite a bit, and the company in its current form has been around since 2016 or so, and that's when we built our first prototype system. That system used pure silicon as the storage media, and the storage media was basically these bathtub-sized crucibles containing silicon, and nitrogen was used as a heat transfer fluid, right? It was coupled to a Stirling engine, 30 kilowatt power generation through it. And then that was scaled up a couple of years later in the form of what we call the TESS-in, thermal energy storage system for the industries. That system was a 6 megawatt hour thermal storage system coupled to a gas turbine producing about 180 kilowatt of electricity. At the same time, we had some interest from SA Water, which is a wastewater treatment utility company in Adelaide, and these guys were looking for a use case for the biogas they produce from anaerobic digestion, and they use gas engines to combust that and produce electricity, but they wanted to do arbitrage on the grid. So just as a proof of concept, we took the same box, the TESS-in box, replaced the heating elements from the top, replaced that with burners, and we built the gas test unit, which is the one on the right. This unit was actually connected to the national electricity market and producing 180 kilowatts of electricity. All three units functioning perfectly fine. There were certain challenges though. So in the last week's conference at HILT, CRC, and also over here, people have talked about the hot blast stove in the steel industry as an example of a thermal storage unit, right? And same thing applies to the regenerators that are used in the glass furnaces as well. The problem with these systems are that these are not designed to be thermal storage systems. These are just plain regenerators. Now, firstly, the checkered bricks that are used in these hot blast stoves or the regenerators, these are lower conductivity material, right? They're not designed to be operating with a very large delta T across the bricks. They're not designed for very, very fast ramp up to provide to the process. The average utilization of the thermal energy storage bricks in these regenerators is actually quite tiny. So the storage density you get is quite low. If you're trying to put a commercial system into an industrial process, footprint is one of the biggest impediments, and that's why you need a very high energy storage density. Secondly, there's the issue of the scale. The scale of these regenerators can be quite large, but then you also have to heat them up using some other source, alternative source, not fossil fuels. And we've been addicted to the fossil fuels. We've been so hooked on to the fossil fuel, the high energy density fuel that we can just burn and burn a natural gas feed which has a flame temperature, adiabatic flame temperature of 1900 degrees Celsius for producing 38-degree water in our home, right? We've been spoiled for luxury. And that's why these regenerators with a very, very high delta T across the flame temperature and the bricks, you can heat them up very fast. So in these thermal energy storage systems, the challenge is not just recovering the heat from them, it's also putting the heat into them in a fast way possible, right? So we realized all of these and looked at these boxes. What came to the front was the scalability of these boxes is quite poor. Secondly, when you're trying to couple an electrical energy source at 1400 degrees Celsius, then you need to be able to absorb this heat as quickly as possible into the storage media, which brings into the thermal conductivity aspect. It is quite understated how important thermal conductivity can be for thermal energy storage systems, right? So we went back to the drawing board. How can we take the very good properties of pure silicon, which is, by the way, one of the highest latent heat energy materials that is available to us? How do we take that and convert that into a form factor which is mass producible and can be put into a system that can be built for very, very large scales? And that's where the hero of the day comes into the picture. That side brick, the one, not a full-size sample. I have a quarter brick, which is a easier to carry sample with me, still quite heavy. The full-size brick weighs about 6.5 to 7 kgs. The one I have is about 1.5 kgs. So that brick is a form-stable brick which contains a silicon alloy inside, which undergoes melting and solidification. The outside still remains the same and looks like a refractory brick, and it holds its shape. And that is what our core technological development has been. And the side bricks can be used in many, many different ways. The first one is your hot gas generator. That's your typical use case where you can provide heat to industrial processes directly in the form of air. We moved away from the original concept of using nitrogen as a heat transfer fluid. Air is, at the temperatures we're operating at, air is one of the easiest available and best integration possibility for the industries that we have, right? So this side brick is compatible with air as a heat transfer fluid as well. We've been able to prevent any reaction between the air and the storage material, that's pure silicon or a silicon-based alloy. We've been able to avoid that interaction completely. It can also be used in electric reactors, where you can line these reactors, and the reactor wall itself acts as a thermal storage media. And the last but not the least is the regenerator concept again, right? I'll talk about the first two in the following slides. So,
Just be where you nearly at.
yeah, sure. So the Cyborg demonstration module, that was our latest generation box. And this is at a 1 megawatt hour capacity. This is still in Tonsley at our workshop. You guys are welcome to visit it. This was funded by Woodside and the Australian government through the Modern Manufacturing Initiative grant. I'll show a couple of results from the box. So what you have on this slide is the same box being used to provide different outlet temperatures from 700 degrees to 900 degrees. The limitation on the 900 degree is not from the box or the bricks. The box itself is capable of providing much higher temperatures than that. It's the heat exchanger, which is the mimicking the customer process for us. That is a metallic heat exchanger. Everything is easy and nice and cozy when you can use metallics. As soon as you go above that, things become super complicated. So as you would notice over there, throughout the discharge period, the variation in the temperature from at the outlet measured at the heat exchanger where the customer process is, the variation is less than plus minus 2 degrees. there's a use case I've displayed over here. I'll run through this very quickly. The charge and discharge are decoupled in this system, so you can choose when to charge, when to discharge, and arbitrage on the grid. The bottommost graph shows outlet temperature. This is a 6-day run, and the box is providing 24-hour heat 24/7 to the customer plant, and only charging during the lowest price period. And this is all automated in the system. Another use case over here was coupled to a profile where you have the power supplied to the system is in the form of a renewable energy curve, so the wind plus solar generation from an actual week in South Australia, and we were able to provide 100% of the time heat from the box. I'll cut through all of this in the interest of time. I've run out of time here. Just wanted to quickly highlight a new project that we've started, which is on the hydrogen production side. So I mentioned that these bricks can actually be used in integrated reactors as well. So that use case, we've just started to work on this project called CYPHER. CYPHER stands for Cybrick Integrated Pyrolytic Hydrogen Reactor. It is a CRCP funded program in which University of Adelaide, RMIT, Canthil, and Woodside are partners with us. And we would be demonstrating the hydrogen production in a liquid catalyst at about 1 kilogram per hour scale in the next 2 years' time. Thanks very much.
I'll invite the rest of our speakers back to the stage. Now, I noticed there were just a couple of questions on Slido, so please feel free to put anything else on there. Try and keep an eye on them on my phone as well. So maybe while others are putting their questions on, we might start with one for Matt. So, Matt, you probably see the question down there in front of you. I guess it relates to the rate at which we can ramp up and ramp down the heater in your system. What's the response time like? And I guess the point of the question is, what's the opportunity for taking advantage of variable electricity?
Yeah, it was something that we noted yesterday in the talks. I think it was Chris and Dan were talking about the need for flexibility within industry because of our technology. Residence times are pretty short within the plant, so we can shut off very quickly. We can shut off almost instantaneously and start up instantaneously. Heat up rates, because we don't use hard cast refractories, can be pretty fast as well.
Right.
Sort of minutes, 100 degrees in minutes sort of thing.
Good, thank you. And Sara, there's one there for you too, I guess. Is 100% Hydrogen-DRI possible? Do we need other forms of energy to overcome the endothermic reduction reaction between the ore and hydrogen?
According to Tenova, they say that they don't need any additional heaters for the 100% DRI, Hydrogen-DRI. With the Midrex process, they do have a heater in their full 100% hydrogen. And they start that round about 70% hydrogen.
Great, thank you. Another question now here, I guess trying to get two of our speakers together. Can we use the silicon bricks hang on, it's changed. Could a curve Cybox bricks around a Calix reactor tube? So I don't know who wants to tackle that one. Have you guys talked before?
We have. We have, and we're exploring those opportunities together. The thermal storage system makes a lot of sense in the DRI side of things. I had a last slide over there which was dealing with how we envision in the next 10 years or so that when the technology develops, how this integrates into a steel mill, where the Cybox side is used for the preheating of the fuel gas, which can use up to about 20% of your lower heating value going into the shaft furnace. And the CYPHER is a hydrogen producing agent for you.
Anything to add, Matt?
I mean, it's covered all the points, really. Yeah, we've discussed it in the past, continue to discuss it. Yes, preheating is a really interesting opportunity for the technology.
Great. So I wanted to get into, I guess, maybe some of the issues, and we'll come back to Slido questions. We've got another 15 minutes to go. So, I mean, by no stretch am I an expert in iron and steel, despite my one-day course with Jeff Brooks, which gave me a sort of step change in my knowledge. Well, sometimes I think I just got more confused, to be honest, Jeff, I'm sorry. There's just so many options, you know, to me as an outsider, so many acronyms, and I guess I'm starting to realise that one of the issues is that there's just the diversity of potential processes, the diversity of ores, of mineralogy, is just overwhelming. And you know, as someone from HILT, if I compare that to alumina, where in some ways, you know, that process is, to me, is much clearer. The starting point seems much more homogeneous. The end point seems very clear as well. And I think, you know, having in the alumina industry, having a very well-defined set of specifications around what you can put into a smelter, whereas in the iron and steel business, it seems to be that you know, you've got different customers that want different things, that are trying to produce different things, and it just creates this massive amount of complexity. It seems a massive barrier to me. How do we tackle that? I'm not quite sure where to start. Maybe Sara. Sorry. I mean, I'm sure it's something you've thought about. Put you on the spot.
Yeah,
sorry.
I'm also a proponent of looking at the current steelmaking process and looking at trying to improve the brownfield sites. Done a lot of work on looking at blast furnaces and what can be done there, whether it's hydrogen injection or natural gas injection, and how to actually bring down the CO2 tonnages. The same with the electric furnaces. One of the biggest things with them is electrify them. If you can get renewable energy, I think 2023 we would have saved 212 million tonnes of CO2 just by turning on the green power to the furnaces.
Yeah.
I see there's well, about the implications of hydrogen costs. I think we've got a big problem moving forward. You know, hydrogen technically is the way to go.
Yeah.
But we are constrained by the renewable energy and therefore the hydrogen production. And scale up is going to be a big issue. So we're going to have to do it slowly. But as we were saying earlier, the scrap availability, good scrap, is not there. And people are looking at ways to improve the scrap. They're looking at ways of trying to pull residuals out, but it's not happening.
Yeah, I mean, I think I totally agree. The electrification push is on in a multitude of different sectors, and there is a lot of competition in the market for that green electron. To a certain extent, the Australian conversation about that is a bit different to the one we have in New Zealand, and I think the one that happens in a lot of the rest of the world, in as much as if you are close to a high voltage grid that is a national market, then there is always an opportunity for anyone generating electrons to sell that on the grid. And that is likely to, and that's a price set by all of the rest of the market. We're in a supply constrained environment. That price will be reasonably high. It will be a lot higher probably than your cost. If you're in Western Australia and you're isolated from the majority of the market, then maybe that's a different game, and maybe then you are talking about a cost-based system. But hydrogen prices, I think, in a lot of the world are going to be limited by the fact that everybody else wants that electron to charge their car, run electrode boilers or heat pumps or whatever it else is coming into the market, and that's going to be a real challenge.
So Martin, if I understood your presentation, Primetals is developing 3 completely different processes, and I just, as a technology developer, is that an opportunity because you've got 3 different products to sell, or is it just a challenge because you're trying to put resources into developing 3 different technology pathways separately?
First of all, to be clear, one of those technologies is Midrex, which isn't really being developed by ourselves,
Okay.
but your point's still valid. High 4 and High X are ours. I guess then the answer is it's not wise to put all your eggs in one basket, really, and that's the approach that we're taking. In some discussions that I've had, I've almost been challenged the other way around. Why aren't you doing this sort of alternative iron making process? And the answer is, well, the ones we've picked are the ones, arrogantly I'm going to say, we're good at. That's what we've focused on. So you don't see us into electrolysing iron ore because we don't have the experience on that.
Great, thanks, Martin. And Chris, you talked about the challenges of, this is going to be a question for Craig, but I wanted to sort of introduce it by referring to some remarks you made, Chris, around the challenges of doing some of this work at larger scale. It seems from the presentation you made, Craig, that you've taken advantage of facilities overseas to try and get to that larger scale. So I'm just wondering, is that good enough? Is that okay? Or do we need those sorts of facilities in Australia? The technology development's happening overseas, but the customers and the suppliers of the iron ore are here in Australia, and they need access to knowledge and information, I guess. So what's the answer?
Well, yes, of course. You know the answer to this. We do need those facilities in Australia, but you can't do it on your own. And so therein lies the challenge of trying to bring our iron ore producers and steelmakers together. That's, in some ways, that's the biggest challenge of it all. So yes, we do need those facilities, but it's not easy to get them.
No, thank you, Craig. We might go back to Slido for a little while. So a few votes here for the question for Martin. So what smelting research or experimental work would you like to see happening in Australia to help de-risk Primetals smelter package for Australian DRI?
It's a bit tricky for me, this, because I believe it will work. I believe the smelter will work. A bit because of what Chris showed. The smelters at New Zealand, we provided them. They were actually made by HILT, but my company ultimately, we provided them in the 80s, 90s. So I have a lot of confidence in the smelter, but I recognise that confidence isn't enough. We can't take a contract on the basis of confidence. We've got a bit of a gulf to overcome there. What I would say is we've got to have a facility that demonstrates and convinces people that the raw materials here will work in this flow sheet. That's what it boils down to for me. I still think it'll work, don't get me wrong, but if that's the thing that's going to trigger the confidence, then I'd have to support that.
Great, thank you. Yeah, sure.
What about the CO2 emissions from the smelters? Because they're supposed to be around about anywhere from 1 to 1.6 tons of CO2.
We'd have to look at that as well, yes, and get the confirmation of that. Yeah.
There was a question here for Chris. So how important is the titanium and vanadium and the revenues in the New Zealand context? Does this change going to hydrogen?
The titanium's not important to revenue at all. It's not enough to be useful. If you want to go and mine titanium, go and mine ilmenite. This stuff's only got about 8% TiO2 in. It's enough to be really irritating if you put it in a blast furnace, but it's not enough to be useful. That said, as I showed, in a fluidized bed, it turns out to be really helpful in terms of just protecting those particles and preventing them from sticking. The vanadium bit's more complicated. Vanadium is a relatively high value metal. It's about $20,000, $30,000 a tonne as a metal at the moment, and has been quite a lot higher in recent years. But it's only 0.5% of the original ore, as opposed to 60% of the iron. So there's 160 times less of it in the total product. And so from a dollar's perspective, it matters. It's not zero. There have been years in the past where it's been quite meaningful. But the reason that New Zealand Steel have moved towards an electric arc furnace and have moved towards a system which allows them to put more scrap and less iron sand through their system is because the CO2 costs are much higher than the vanadium revenues. That's a challenge when we start looking at this systemically at a global level and we think about what we need vanadium for around the world. We need it for high-strength steels. We also need it for aerospace alloys and for orthopedic implants. And should anyone ever manage to get vanadium redox flow battery business off the ground, we're going to need a lot of it for that. But most of it comes from steel slags, and most of that steel slag is currently coming from very carbon-intensive blast furnaces in the Panzerhütte. So if you move to a system where you're not producing vanadium slags from the sorts of systems we've got at New Zealand Steel, you need to have a think about where you are going to get that from in the future.
Yeah, the vanadium revenue was a nice piece of icing, but frankly, as a steelmaking, it was just a pain in the backside. Okay, so the vanadium needed to come out. Because if you didn't take it out in hot metal pre-treatment to make the slag, then it just reverted like hell when you tapped it into the ladle, and it gave properties to the steel that you for flat products was not helpful. So that's the plain facts about vanadium.
There's some fairly technical questions here. Let me pick one of them. This is, I guess, for Mahesh. What's the minimum viable size of a silicon bricks installation? What components are prohibitively expensive at small scales? Could it be used as a low capital cost installation in preheaters to make use of free or curtailed energy? It's the one at the top there now. Can you...
Installation. I heard insulation. I was like, this is the complete opposite of what we're doing. We're focusing on the higher conductivity and the higher energy density, and wouldn't want to use it as an insulation material. Now, coming to the smallest installation size. Now, the smaller the system, you have lower amount of volume of storage compared to the surface area on the outside, so your losses are higher. So you need to get to about a reasonable scale before you can get 90% plus efficiencies on the thermal side. And that size is about 40 to 50 megawatt hours. Below that, you would start to lose a bit of the efficiency. If you're okay to take that efficiency penalty, then you can install smaller systems. Otherwise, we envision that in the industry, you would be looking at that sort of a 50 megawatt hour modules and multiples of that, scaling up beyond gigawatt hours.
Okay. Thanks, Mahesh. So we've only got a couple of minutes left. I wanted to end on this question. My teenage son loves a good scam, and so we've got a like-minded person out here in the audience. So the question is, what stops anyone producing high-emission steel then immediately reprocessing it as scrap to claim it as a low-emission product?
Some people are doing that. No, a lot of the steel makers now are using their own scrap that they produce in plant as part of their recycling. I don't think anyone's gone quite so far because of the economics of scrapping your good steel out. But and a lot of them are also buying the scrap from their customers when they know they've got good steel. So there's a lot of purchase of their own materials back when people are doing stamping processes and things like that.
I've got a cynical slant on that. Yeah. So, yeah, I find it a bit ironic that the US steel industry claims it as being so green with their scrap melting. But, every tonne of that scrap came from the blast furnace process. So, they've already spent their CO2 all those decades ago. And so, okay. Yeah. Yes, they look green now, but they're not.
But if you look at the effluent out of the United States, it's half of China, and we've got 73% EAF, so there's a whole bunch of other problems with the US. Trump's going to make it.
Anyone else want to weigh in on that one? No, I said I'd finish there, but there's a last-minute question here that I think we'll put to you, Matt, because I was curious as well. What's the reason for Zesty can process low-grade ore?
I think there's a few aspects. One is that because it's not pelletized, because it's a fine material, doesn't have the same issues with sort of pelletization, breakup, and whatnot. So that's one aspect to compress is very fine materials as well. I can't really speak to why others are struggling so much, but we're getting high metallization, good smelting behaviour with the ores.
Okay. Well, great. Thanks, everybody. I think that's been another great session. Thanks to all our speakers for their contributions and for the great questions in the chat. Thank you.